On slide 24, we turn to bivariate analysis. And the first model we show here is the random intercept cross-lag panel model. And it's shown in two different versions. On the left, it's portrayed in the way it has been set up traditionally in programs like Mplus. That is, we introduce these factors to capture within person variation, so variation across time, free of the random intercept influence. The random intercept influences the observed variable, and the observed variable is also influenced by the within part. So you have the between part and the within part. And that's the old approach, using factors to explicitly create a factor variable representing the residual going into y1, because the measurement error is 0 up here. On the right, we have the new approach using hats, so we don't create any latent variables. And they are created automatically inside of Mplus, and that particularly benefits Bayesian analysis, which is the primary estimation technique when we turn to categorical outcomes. So here we don't have to draw circles. You can if you want to, or maybe small circles, but no circles at all seems to be just fine. So we have these cross-lagged effects among the residuals and with the covariance between them for all time points. A little bit simpler drawing. Now turning to the RI-ARMA model, which is the new model that we've introduced in this paper, which is suitable for a longer time series. Probably you need at least 8 time points. You have the same situation as in the traditional way of representing the residuals, namely by factors. In this case, we don't have access to the y hat, the hat notation. It would actually require a double hat, if anything. So we have to define these latent variables again, and with measurement error 0. Because we want to be able to regress, say, take the third time point here. We want to be able to regress y on z and z on y, but we also want to be able to work with the residuals, namely the residual of fy2 influencing fy3. That's this path here is the moving average part, the residual at an early time point influencing the variable at the later time point. And same thing for the z part, that is influenced by the residual of fz2. And these residuals have correlation between the two processes across time. And once again, we don't include a moving average part from the first time point, but only from the second. Now this is a simple version of representing the RI-ARMA. The fuller version, which is also discussed in the paper, is when these MA components also have cross-lag relationships. For instance, the fy3 component here could be this residual could be regressed on the residual at the previous time points. So you have these cross effects between the residuals as well as between the variables themselves. But that is a more complex model with more parameters and would then require more time points. So this is a parsimonious model that may be sufficient. Now turning then to slide 26, we take a look at the results for the bivariate analysis of this data set of depression and self-esteem, 5 time points, sample size 663, that we did the univariate analyses for. And on the left here you have the whole sequence of models in a similar notation from the univariate analysis. Although in the univariate analysis, instead of using the word CLPM1, we use AR, auto regression 1, lag 1, and auto regression lag 2. Similarly, I used RI-AR1 for the univariate analysis, but here now we're doing a bivariate analysis. So if you like, you could just add CLPM at the end. So RI-AR1 CLPM, or RI-CLPM1. But so it should be understood that all of these models are CLPM, that is cross-lag panel models. I just didn't want to tack on the CLPM suffix for all of these acronyms to make them that much longer, and I wanted them to be similar to the univariate slides. So I start with the model 0 here, where you have the cross-lag panel model with the lag 1, so it's an AR1 model for each of the two processes. And the invariance refers to the autoregressive parts and the cross-lags, not the residual variances or covariances. And this is the model used in Ort's paper. And it has 29 parameters here, and the MLR chi-square with 36 degrees of freedom is 207. So a clear rejection of that model. It's not a model that fits the data well. The root mean square error is too high, and you have probability 0 that it is less than 0.05. So we would reject that model and not interpret it because it's not close enough to data. This model, CLPM1, allows for time-varying auto-regressions and cross-lags. And it looks like we reduced the chi-square a little bit, but we also reduced the degrees of freedom because we've gone from 29 to 41 parameters. This model is also, in my view, clearly rejected. And although the RMSEA seems to obtain a good value. But I would say we can rely on chi-square here, and this is not a well-fitting model. We could add a lag 2 for each process. And in fact, we should mention that the two processes don't have to have the same lag. In fact, they don't have to have the same model. You could have, for instance, a CLPM or AR1 process for one, AR1 model rather for one process, and an RI-AR1 model for another, for instance. I'm not saying it makes sense, but we don't have to have the same models. But we're going to entertain only models that are the same for the two processes. So adding a lag 2 certainly improves chi-square quite a lot. We get a non-zero value in the p-value here. And of course, you can take the difference here between the two models with 6 degrees of freedom. You can create a likelihood ratio chi-square test, 2 times the difference here, which is hugely significant, pointing to lag 2 as being the better model. However, we can get better fitting models with lag 1 if we go down here in further modeling. We have the RI-ARMA model, auto regression of order 1 and moving average terms of order 1. And that's a model that fits quite well. Now it has 50 parameters, so it has more parameters than the CLPM2, but it fits very well with all measures, according to all measures. Now the dynamic RI-AR1 with 44 degrees of freedom, so 44 parameters, fits well as well. So you have a p-value 0.05 plus here. So that is a dynamic model like the previous ones. And you have the dynamic RI-ARMA model as well here, which goes up to 52 parameters and fits well as well. So those are the dynamic models, and among the dynamic models you have the best big for, let's see, 3349 for this dynamic RI-AR1. But the RI-ARMA model is not bad either. Now turning to the non-dynamic models, we have our RI-AR1, which is the same thing as an RI-CLPM with lag 1, the standard RI-CLPM. And that one fits quite well. 21 degrees of freedom, 34, very similar to the to model 4, 21 with 33, basically indistinguishable models. So there you have a choice in terms of substantive theory. Which model is it that you think makes more sense from a substantive point of view? Statistically, they are essentially indistinguishable. Now you could go to the RI-ARMA model as well, although we have only 5 time points here. So it is really too few time points to work with this model, which has 50 parameters. So you get a chi-square 15, that's 9, and as I said, I'm always suspicious of models that have lower chi-square value than the degrees of freedom. It seems like overfitting. It has too many parameters, but it is possible to analyze it that way. So there you have a set of models. If you're interested in random intercept models, which I think is a good idea, you have the RI-AR1 or the dynamic RI-AR1, depending on whether you want relationships between the residuals over time or between the variables themselves over time. 2 different substantive interpretations. With more time points, it's possible that we can tell them apart, but not with 5 time points. I should also mention that in some writings for the dynamic RI-AR1, like Bolen and Brandt and Cipher, it's recommended that you free the first loading of the random intercept factors from a substantive point of view, or from a modeling point of view. The first time point is different than the others because it's not influenced by anything previous. So, and when you do that, in this case, you don't get much of a difference. You may in other situations, but not here. So then let's take a look at Mplus outputs here and go through different models and discuss them. No, I think I'll do that in a separate stage.